Okay, let's get started. First, welcome everyone to join our Bruker's Symposium. We are focusing on nanomechanics for the technology and their applications in different research areas and also some industry like semiconductor. So first of all, I would like to give a brief introduction to our Bruker nanosurface and metrology division. My name is Weigang Chen, Weigang, based in Bruker Guangzhou office, covering the South China territory for AFMI, and other surface analysis product. And sorry. Bruker is one of the leading manufacturer for scientific equipment. We have many different kinds of scientific equipment, range from biospin, which is covering nuclear magnetic resonance or EPR, and also we have another division called CARIT, which focuses on chemical analysis. It includes mass spectroscopy and FTIR or Raman products. So for CARIT, it's focused on giving chemical information. And the third division of Bruker is called Bruker Nano, and it includes our Bruker Nano Surface division with product such as AFM, optical microscopy, nano-indentation, and also some other products such as XRD, EDS, and EBSD. The smallest division of Bruker is called BEST, and it's not very often seen in China, but it focuses on superconducting devices and some big science research facilities. For our division, Bruker Nanosurface and Metrology. So from this name, you can see we focus on nanoscale and surface and metrology. So we have various technology to characterize the surface roughness, critical dimensions, mechanical properties, or electrical properties. So our product line ranging from stylus profiler to optical profiler, which are on the left side, which is focusing on the surface roughness or step height, critical dimensions, surface roughness data. On the right-hand side, you see we have some chemical mechanical polishing systems or tribology testers, and also nano-indentation, nano-indenter, which focusing on the mechanical properties or tribology properties, ranging from nanonewton to Newton or even to kilonewton force range. And in the middle, you see we have AFM and also FMIR, which is combining AFM with chemical imaging function. So here is just to show a general overview of our product line, but I will not go into details. Later, we have 3 different talks given by our application scientists and experts. As the equipment, especially for research labs, the hardware is one very important, but more important is whether we can support you well. If you have some very complicated equipment or experiment, or you see some very good publications on top journal, so you may ask, hey, whether we can get it done on the AFM in your lab, on the nano-indentation system in your lab. So we have a strong team to support you. Here is the group photo of our division, which is back in December last year. So we have close 60 members, and among them, you see we have the biggest group is our service team. And later, Dr. Sun Hao, who is the sales manager, senior sales manager of China, will give a more detailed information about our sales, our service and support system. And we also have a very strong application team supporting different kind of products. And among our team members, we have around 20 members who have got PhD degrees from different research areas. For example, for me, my major is material science, focusing on ferroelectric material. And here, Dr. Liu Yang and Dr. Shen Hao, we all have different research backgrounds so that we can support not only physical chemistry, but also biology. Dr. Cao Xu, he is actually graduated from this university, University, with a biology background. So with this strong team, we have very strong confidence and the capability to support the research, the experiment needs of from different subjects research, different institute with our equipment. Okay, for our products in Hong Kong, actually we have more than 55 systems installed in Hong Kong already. More than 20 AFMs, and for material research, such as damage icon, damage edge, Innova, or Mode, focusing on material side. And we'll have 12 nano-visitor bio FM, and also one optical tweezers for bio researchers. And also 12 nano-imitator and travel testers, and also more than 20 stylus and audio profiler. So with the large installation in Hong Kong, we also have our very frequent and strong support for our customers in Hong Kong. We have a regular service and application centers revisit, and we carry out AFM basic training in Hong Kong UST in June 2023, and after that, in 2024, last year, we carry out the advanced training focused on electrical modes, right here in SPF. And this year, we will carry out the advanced training on Nano-Mechanical. So here is some photos of the basic training in 2023, and some photos of the user meeting and the training in 2024 last year. So we invited Dr. Xini, Prof. Leslie, and Prof. Lu Yang from Hong Kong U to give us some deep talk besides our other talks provided by our application scientists. And you can see in last year's user meeting, the attendees, we have a large group of attendees and researchers from different universities across Hong Kong. So, in the last, I would like to give my many thanks to MSPF, to Dr. Shi and Gordon for their very generous support of this activity. And also, I would like to thank Tata for his strong support and a very swift local response in Hong Kong. And later, Dr. Shen Hao will give a very brief introduction of our service systems.
Okay, thanks, Wei-Gang. Yeah. Welcome to this workshop. I'm Sun Hao. I'm a service director, China Bruker BNSM division. And it's my pleasure to be here today to introduce Chinese service resources to you. To provide better support over the years, we have expanded our customer support capabilities. Actually, in the past 10 years, we have expanded our team size. We increased the number of our service tools, and we established 2 customer care centers in China, and we also made a relatively comprehensive customer support system in China. Let's go to the details. Here is the China service team. We have 2 field support teams to do the installations and on-site troubleshooting. And we have a global support and customer care center team leading by Dr. Liu Yang. This team is focusing on the second level technical support. And we also have an admin team to deal with your orders and contracts. To provide a better and quicker support to our local customers, we set up a customer care center in Beijing in 2011. And Shanghai Customer Care Center was just opened in March last year to provide better support to our South and East customers in China. And our customer care center's core functions include social media, phone, email support, the local test repair service, customer and internal training, and special research support. We recognize the importance of staying connected with our customers. So our WeChat, WeCom service provide instant support through 22 WeChat groups with over 7,000 customers. We discussed hundreds of applications and operations questions every day in these groups, and we share the training notice and the research paper recommendations in these groups. And there's also an FAQ system which can provide you quick answers for some frequently asked questions. You can see this is a FAQ system. You can access it in the WeChat groups. And the local test and repair service is to reduce the downtime of your tools from months to weeks. We covered a wide range of product lines, and we have capability to test and repair most of the parts in local. And to address the parts shortage and long repair time issue, we set up a local warehouse in China to make sure the quick turnaround of critical parts. And the continuous customer training is also very important. So we are committed to providing 10 offline customer trainings every year, and at least 3 in Hong Kong, Guangzhou, and Shenzhen. Here are the photos about 2023 AFM basic training in HKUST. And our customer training system is designed to the customers at different levels, from the installation training for the beginners to the advanced training for the experienced users. We ensure that everyone has access to the knowledge they need. And our local knowledge database on Yuque platform provides over 200 FAQs and over 800 technical documents in Chinese. We have also invested in creating a library of online training videos, and they are available for free on the Bilibili website. Here you can find the operation principle trainings. So you can find the application webinars and some short training videos about simple troubleshooting. And our cooperation with the customer beyond just product support. Actually, we aim to provide solution to our customers. We want to add values to our customers. So we cooperated with our customer to publish the research papers, and we make the paper collections every 5 years. In the 2020 collections, we have 52 research papers published with our customer together, and now we are working on the 2025 version. And to make customers find support easily, we made a service card. And on this card, you can easily find the standard service process on it. And you can just scan some QR codes to access all the available online service resources. Here is the summary of the customer support system. Compared to other regions, the China team provides more featured service, and all these can be customized in our service contract. As we look into the future, we aim to be your trusted solution advisors, and we look forward to the success we will achieve together with you. And thank you for your time, and enjoy the workshop. Thank you. Back to Wei.
So, okay, next we will have a first presentation from Dr. Liu Yang. He will bring a topic about the quantitative nano-mechanical and the non-scale chemical characterizations based on the AFM.
Thank you. Thank you, and thank Dr. Sun and for good introduction. And welcome everyone, and give us a choice to briefly introduce our techniques. And this week we already discussed some techniques of our AFM nano techniques. Use this AFM probe, the small probe, to detect the large size. And so my topic today is just the same topic as we have in this week's, and I would briefly introduce the application of our nano-mechanicals, and then we would correlate it with the chemistry characterization done by our IR systems. So briefly, the AFM, everybody are experts here about the AFM. So AFM, the name is a microscope. So it is imaging tools to give you the distributions of the of our samples. And as such, at the beginning, this is invented in 1980s. And at the beginning, we just want to say what the surface looks like. And then after several years, people want to get more information. I know you are beautiful, but I do want to know what you look like inside. So people started to think about, hey, if I can use the AFM to detect rather than morphologies, they want to know some properties of your samples at nanometer scales. And at the beginning, they still want to use the AFM to serve as a microscope. So they want to use the property of different materials to say, okay, what's the different components distributed inside my materials? And then we invented more and more materials, and we think the properties at the nanometer scales and the macro scales, they should not be the same. So we want to say, okay, I invented some fantastic things, and I reduce its size to nanometer scales so hard. I wanted it to be different. So we started to think, okay, if I can use this nano technique to detect the property at the nanometer scales. So briefly, we have the two tasks. First, we did imaging. From the image, we know the distribution. Second, with this technique, if we can get the parameter out at the nanometer scales. So the first thing we do is from the name, the atomic force. Okay, if somebody call it a force, we should be able to use this serve as a stylus to get some mechanical properties. So basically we just capture we just learn those knowledges from our previous great scientists, and to say if we can study the mechanical properties using our AFM probes, and in the bulk mechanical study, we starting from the Hooke's law, and then we go to the stress and the strain, we get the modulus out. So at the nanometer scales with the AFM, we should be able to do similar things. So we also want to use AFM to detect the mechanical properties. Of course, the holy grail is the modulus at the nanometer scales. And then from that, we have many customers in various ranges. We have biologists, we have polymer science. They told us, okay, besides the elastic world, we have viscoelastic world, and we should do more things about the time-related mechanics. So we also introduced the dynamic microscope analysis into the nanometer scales. Now we are be able to use the AFM probes to study the various properties of our materials, including modulus, including the time-related modulus, which is viscoelasticity. So my topic today is we give a brief introduction. I'm sorry, should be a review because you guys already understand this science very well. So brief review about the principle, the nanomechanics, and then I give you some examples of using the AFM to first get image, get components, and the second, we should be able to say the property. We should get some quantitative numbers, and the third, we may want to go back. I know chemistry in university, and my professor in the university told me, okay, you should know what you are doing, and you should know the chemical structure at first, and then goes to its chemical and the physical properties. But AFM is kind of, the AFM probe is blind, just like that. They don't know what they're going on, so they need some other guys' help, like IR or something to help you. What's the chemical properties? What's the chemical structures of the samples? So we goes back and related the AFM techniques with the IR. Okay, so first about some principles. The AFM principles is we learn from our the great scientists named may go back to Newton and Hooker, and our idea is we want to learn the mechanical properties of the sample. The two main components, they are the interaction force. We want to know the interaction force between different components. And the second, we need to know its property. The K is the modulus. So our idea is use the AFM probe serving as a stylus. It compresses the sample, and we measure the force, and we capture the deformation of the sample. And from that, we use the classic Hooke's law to get the stiffness out. And then with the help with the great hertz, we can search back, we can calculate the modulus out from the stiffness we measured. And that's the whole idea of the AFM-based nanomechanics. And starting with that, we we developed a different kind of techniques to start to measure the stiffness, and then use Hertz model to search back to modulus. The most important or the key one is the force curve, and then we use the force curve techniques to develop mapping techniques. We did force curves at each point of the samples, and then I can get a modulus mapping with my results. And of course, the purpose of our instrument company is we just want to serve a good partner for our users, and we want them to use our instrument more friendly. So nowadays, we reduce the calibration process a lot using the new techniques. And when I joined Bruker, and I learned how to do the calibration manually from Dr. Sun Hao. And usually took several hours to do the calibration, and then just a few minutes for the final images. But nowadays, it's much easier. And in 2017, we developed more skills to try to expand the AFM techniques to the very super hard samples, because the original we just used probe to compress the sample, but the AFM requires high resolution, so our probe is really sharp. As such, it will generate a giant pressure on the samples, and such giant pressure will damage the probe nor the samples. So we need to find another way to study those high stiffness or very hard samples. And we also goes back and to learn the something about the acoustics. And from the acoustics, we get the contact resonance principle. And my wife gave a story. When she goes to the supermarket, she wants to find out which watermelon is good. They should just press it, because the different watermelon, the mature watermelon, it has many waters inside, and the immature watermelon is more like a solid, more like stone. So when she pat on it, she can hear different sounds, and from this, of course, you know, the sound is just it's different resonant frequencies. So from that, she can distinguish immature and mature watermelon by the stiffness. So we took the watermelon principle back to the AFM. So if we use a probe to touch the samples, the hard samples will give a higher frequency, soft samples will give a low frequency. As such, we don't need to press the samples, but to use the daily knowledge from our life. We developed this contact resonance AFM, and we use that to study very hard materials. And then we use that techniques also for the mapping and the modulus calculation. It's very consistent, and some of our customers, they are from the School of Engineers or from the maybe ancient lives. They use that to study fossils, something like that. It's quite good techniques. And besides, or on the contrary to those very hard samples, we have some customers, they are doing some soft stuff. They are soft, but they are smart. Those property for some polymers or some hydrogels or some biomaterials, it's not like a solid. It does not have a substantial crystal structures, but their polymer chains can vary as the time. As such, they define their materials. The modulus or stiffness should not be constant. They would change with time, and they call this property viscoelasticity. And the classic viscoelasticity is usually studied using the famous dynamic mechanical analysis, the DMA. And the DMA is, I I saw and Dr. Shi introduced our the MCPF facility yesterday, and we saw we can do DMAs using thermal method. We can do with the mechanical method, but the DMA is just at that start. In previous study, we use a giant stylus, but nowadays we can use again AFM as a stylus to do the DMA at the nanometer scales, and then we can capture the viscoelasticity property at the nanometer scales. And so that's about our principle. So the whole idea is use AFM probe to get the stiffness, and with the help of the contact model, we get the modulus. So let's maybe go to some examples to about these applications. So our first and topic is about the polymers, and the polymers is the polymers is it has various and structures and its properties. For example, its modulus can vary from megapascals to some tens of gigapascals. So, and the polymers is also widely used in our material, in our daily life. And the good advantage of polymer is it's not a single one. We can combine it with other materials, with other polymer materials, and to make a lower one. And it can really reach 1 + 1 is larger than 2. So a good structure, a good example is the polymer blend consisting the polyethylene and the polypropylene and the polystyrene, and this is widely used in your car. It's for it's in the car, and from this, and we need to know how these different polymers they are combined with each other, and the AFM images can serve as a good example. And because the polymers, if we look at the surface, it's boring, it's a plain and a rough surface, and I don't know what I'm looking at. But then with the help of the Nano-Mechanics, I can use the probe to measure the modulus at a different point. And as such, I can say, okay, I can clearly say from this modulus mapping, there are 3 components of my sample, and the 3 components, their modulus are significantly different. And besides that, I can even calculate the quantitatively modulus out from it, and then we compared with the bulk materials to say, okay, which material is which material is which polymers. And in the polymers, I think that's the one industry or the one region that people want us for consistency. Bruker did a good study. They studied the different polymers, the various widely used polymers in our daily life, and they measured the modulus at the nanometer scales, and then compared with the bulk materials. I think this one would be only accepted in the for this kind of application, because you guys are the scientists. You don't want your work to be same with your predecessors. You want to be different. I invented my things. I went to the nanometer scales and then I do the measurement. I found, okay, I'm the same with hundreds of years ago. What I'm doing? But in polymer size, we want to show, okay, Bruker not give you bullshit, but give you some substantial things. So use this example to say, okay, they think are substantial. You can trust these numbers, and then you can go to your unknown work. And we also, as I said, we also introduced the techniques goes to the viscoelasticity, and I remember in a famous professor, Dr. Zheng Qiang in Zhejiang University, he explained the viscoelasticity very well. The K of viscoelasticity is just the time. When we consider time, the modulus or stiffness, they should not be constant. And our idea is we don't want to waste the precious time of our customers. We don't want you to stay there to watch, okay, how this modulus change. We did something, how it's just a smart way done by our previous mathematics, change the time domain to frequency domain. So instead of watching the modulus change with time, we show you the modulus at different frequencies or different speed. And at different frequency or different speed, we say the same thing as we expect in the time domain. As the frequency increasing, the polymers should be looks like more stiffer, just like water. And we in our techniques, we can use our probe to compress the sample quite slow or quite fast. And as such, we can study the time domain or the viscoelasticity of our sample. And for the AFM images, we also need to think about the influence of our probes on the sample. Usually, when I am a rookie on the AFM scale, on the AFM territory, and I just learned to do the my first topic in the university is to study some nanopillar structures, just like those photos on the surface. And my professor gave me this topic to study what this nanopillars looks like on the surface. And I found my lab mates told me, okay, I made some fantastic structures. You should be able to see those pillars clearly. But when I do the AFM, I should not say, I just saw any surface. And then my professor told me, okay, you guys, I just at the beginning, you use the too large force, you scratch with everything. And I don't like it. I say, okay, come on, AFM should be give what it should looks like. It should not damage my samples. But he told me, do you know quantum mechanics, right? You are related with the objects. So the same thing happened on AFMs. You use large force, you use small force, you should be able to say different things. So that's what we also observed for the mechanical properties mapping in the using the AFMs. We use the AFM probes, we apply larger force or small force. We should be able to say different things. And this also gave us an idea. If we use larger things, we may also be able to observe some buried structures rather than only the surface. So, and this example is a good example. If we just use some softer or do it gently, you just say, okay, this plane, the phase or the mechanical properties looks the same everywhere. But if I apply a larger force of the samples, I could say, okay, this circle part is kind of softer, compared with the other, this kind of fiber-like structures. So that's our idea of the nanomechanicals. We would change the thing, how it looks like, and the different conditions. And yeah, it served as image scales. It provide a good resolution. That should be its property. Should be its scales rather than to get the quantitative results. So here is the we captured the modulus and some adaptation force of the polymers with those helicoid structures, and using these structures is also clearly observed under the modulus mapping. And for the polymers, it's another significant property is its property will change against the temperatures, and the AFM can also serve as a in situ study of your samples and the various temperatures. And this one is it's a continuous scanning of the polymer polypropylene and the PEO blend. And we study the temperature. We study the temperature dependent structures, and as we increase the temperature, we kind of melt the polymers. Of course, polymer does not have a fixed melting point, but it will be melted down similarly. And then as it melts down, the modulus will decrease, and then we can reduce the temperature back to say the recrystallization process. And yeah, if you just look at the height images, you just say those this needle-like structures change, but with the help of the modulus, we can clearly say as the temperature increase, this as the temperature increase, this PO part, its modulus is significantly reduced. That means it's melting. Okay, yeah, this one. Yeah, and yeah, that's another example of the samples different morphology or different properties observed under different force. And the AFM, our mechanical mapping is also served as a high resolution images. And this one is about arcane crystal, 2D crystals formed on the surface. And with this AFM techniques, we can see the crystal structures, those kind of patterns on the surface from the topography, and it's also observed under the modulus annotation. And we can also do the temperature changing, and the temperature change we can say is recrystallization process. And there are more examples, and so I can I would just jump some of them and goes to the next topic. Is we can use these nanotechniques to study rather than soft polymers, but some hard samples such as metals. The metals is similar. It's kind of opposite to our polymers. It's more solid, it's more substantial, but it also from different blend or combined structures like the polymers. The famous is the alloy. And for the alloy structures, it's similar to our polymer blends. We just say a plain surface, we don't know which is which. And we don't know what's for stainless steel, which phase is the martensitic, which one is Austin stick. So the AFM nanotechnique can serve as this purpose. They just use the AFM probes to measure the modulus, and the hard one and the soft one can easily reveal its identity. And it's also served for some super hard materials like the tungsten carbide. Tungsten carbide is the modulus can go to several hundred gigapascals, so that's really hard. And we usually for those kind of probes, we would use the diamond probes to serve this purpose. And with that, we can clearly say the modulus. We can clearly say the modulus mapping and reveal the tungsten carbide distributions. And for some the alloy structures, they would not easily combined. They may form some intermetallic phases. That means they'll blend together at the crystal level. And use the AFM, we will also be able to reveal that with the help of the modulus mapping. This is another example of the solder, and we used this kind of solder before, and in this solder we would add some lead to reduce its temperature, reduce its melting temperatures. Of course, we are not allowed to add lead anymore. Yeah, for this example, it's about lead with about a solder. We add some lead in it, and we want to say, okay, what's the distribution of lead and the tin inside the alloy? And from the adhesion or the modulus mapping, we can say clearly there are some there are two components, but which one is which is still a little bit hard. So our AFM techniques, the peak force quantitative nano-mechanical mapping, we can combine it with other techniques. For example, the famous KPFM. The KPFM is used to study the potential distribution on the surface. And from the potential distribution, we can capture the work function of our materials. So we combine the mechanical map, we can combine the mechanical mapping and the potential mapping. We can clearly say those soft parts, those large adhesive parts, it has a lower potential. The lower potential means it is there are more electrodes on the surface, so it means it has it should have the lower work functions. So as such, we can know, okay, this part is our lead. So, and we combined the mechanicals with other techniques. It expand the application of our nanomechanicals. And these techniques we can also use for some organic, inorganic combined materials, such as the batteries and the fuel cells. And in the battery anode, and we would usually rather to use one component. We usually will make a blend of several components. For example, in the lithium battery cathode, there are at least 3 materials. One is the lithium oxide, and the lithium oxide, of course, we know it is it is not conductive, and then we would have some carbon nanoparticles. The carbon nanoparticles, it is served as the electrode, so it should be conductive. And to combine the lithium oxide and the carbon nanoparticles, we would use some polymers as a feeder to combine them together. So, and for the batteries cathode, it is key to know how this lithium is transferred inside the cathode. So how we need to know how the lithium oxide is connected with the carbon nanoparticles. So this is a distribution story. We need to know the distribution of the 3 components. So the AFM image is done first. Okay, I get a nice AFM images, but I'm sorry, it tells us nothing. I don't know which one is which. And so we need our nanotechniques to tell nanomechanical techniques to capture results. So, okay, we get a modulus mapping, and okay, it gives a different story. So on this modulus mapping, I saw hard part, which is bright, which is yellow, and I saw some dark part, which is the softer. Okay, from the structure, I know the polymer should be soft. So I would guess, okay, the polymer maybe it's the failure to connect those giant hard islands. Okay, then we did some other techniques to study the conductivity. So we use the conductive AFM and to study the resistance of the samples. And we found, okay, this part, this soft part, some of them, they show high resistance and some of them show the low resistance. Inside our structures, we know clearly only the carbon nanoparticles it is conductive. So we would clearly know in this low modulus, in these soft parts, those are our polymer failures. And here it is the carbon nanoparticles, it is fixed here. And for other regions, for other high resistance regions, it is a pure particle, it is pure polymers. And then those giant ions, we know, okay, that should be our lithium oxide. And that's another story of the fuel cell electrodes. The fuel cell electrode, it also has the several components, and we have a carbon black, which served as the electrodes, and we have the we have the platinum, the nanoparticles as our chemistry, and we use some polymer served as a filler. And this one is done in ethanol media. It's done in liquid, and we use the P4Q and our nano technique to study the modulus map, to study the modulus mapping. And from the modulus mapping, we see some interesting results, and we give a good explanation of these results. We have the carbon black particles. The carbon black particles, it is covered with the polymers. The polymer served as a filler. And the polymer, of course, is quite soft. And the polymer in this cartoon, it is right down, it is marked with the blue puppet. And these polymer fillers may cover our carbon black. And if we are doing the AFMs outside of the carbon black, outside of the polymers, we should sense some soft materials. And if we are just do the study on the carbon black itself, we should sense, okay, there are some quite tough materials, but still there are some polymer beneath the carbon black. So it should be more stiff. It should be stiffer if we are doing the AFM on carbon particles without this polymer failures. So we see this one without the polymer carpet, it shows the highest modulus. And we also observed some no-modulus particles. And these no-modulus particles, we think is unstable particles. It is just squeezed up by the other particles. And if we use polymers, if we use AFM probes to compress on it, we just squeeze it back in. So the modulus, it shows, okay, it is kind of soft one. So it's quite interesting results. The AFM, from the name, we just think, okay, we should be able to say some atom structures with the AFMs. So the atomic resolution, we can also obtain it using the under the Nano-Mechanicals. So we did that on the, of course, on the classic crystal structures, the boring mica. On the mica, we can clearly see the crystal structures of the mica layers, and we can even see those the defect on the surface. And not just and also we capture it, we get it done on the calcite and on 2D materials. That's we can use the mechanicals mapping to get it done on the to obtain the atomic resolutions. And I think the next topic is about the life science, but Dr. Cao Xu will give you a more interesting results and more complex results on this part. So I may jump the life science examples and leave it to Dr. Cao Xu. And I may go directly to the correlation techniques, the AFM-IR. The AFM-IR, I think the AFM-IR techniques is invented nearly 1990s. And once the AFM is invented, we know the AFM is more imaging skills. We need something to help the AFM probes to know the chemistry of the sample it is studied. So basically, we need some other techniques to give the identity of the sample we are looking at. So the IR is it serves as a good one because the IR is first, it is widely used in the macro scales, the chemistry categorization techniques, and of course, Bruker had its good IR. And then we think about, okay, how we can combine the IR techniques with our AFM. The IR, it itself, it is kind of the electromagnetic waves, and our AFM probes is kind of solid. So how we combine the particle or how we combine the solid stuff with the waves. So that's our ideas. So the idea we capture now is maybe we can use some properties of the IR. The IR in our chemistry, it serves to detect the vibration energy of our molecules. And since different molecules has different structures, and the different structures, they would show different vibration. And the IR has the same energy with this vibration energy. So the molecules will absorb IR and its vibration will change. And as such, we can detect its structures. That's the classic IR. But when it goes to the AFM, we think in different way. Okay, a molecule absorbed IR waves and its vibration change. Then what next? I'm sorry, the kitchen chemistry come back again. My wife used the microwaves to heat their samples. So the microwave or the IR, they serve a good thing is once you change the vibration, you change its temperature or you change its shape. So the AFM, those AFM scientists, they think about if the molecule absorb IR, the shape will change due to the vibration change. So if its shape change, hey, that's that's our AFM. We can detect any tiny shape changes. So we shine our samples. We shine our samples with the IR laser, and then we pulse the IR laser, and we pulse the IR laser at the same frequency of our probes. And as such, the whole samples will observe the IR laser. It will cause the vibration change, and the vibration change will cause a small shape change. And then I use an AFM to study the morphology change of my local samples. As such, I detect if this part observed IR light or not. If yes, okay, I can learn the structures from the wavelengths of the IR. So that's the whole idea of the AFM IR structures. So we can just use the kitchen chemistry, its thermal properties of IR to study to combine with the AFMs. So we can we can use these techniques, and then we change the wavelength of the IR. We can get spectrals out with these techniques. And since we are using the AFM probes as a detector, that gives the nanometer scales intrinsically. So, and I think in 3 years ago, we introduced the IR techniques onto the famous icon systems. On the icon systems, we can do all the classic applications done by the AFMs. We can introduce nanomechanics. We can introduce the nanoelectrics. We can capture modulus. We can capture conductivities on this icon system. But now we introduce IR here. We can know the chemical identities of the samples, of the samples. So it makes this it just makes this this techniques like fully functional robot. And so besides the images, we can capture the same thing, the nanomechanics, nanoelectrics, and then we do the nanochemical mapping of this system. And we can show you a good example of again goes back to the polymer chemistry. And a good polymer product is the rubber. No, I'm sorry, is the tire. And the tire is made up with the rubbers, and we need to increase the structure. We should be able to adjust its mechanical mechanical properties by adding some fillers, and to those fillers will change the its chemical structures, and as such change the mechanical properties. So for example, we have some carbon or silicon dioxide, and then we have some polymer chains. And those polymer chains is just like the mud. So our tile, if a tile is just like mud, you can consider it give you a large resistance. No, we want our tile to be more like a solid. So usually people will add some filler to combine those polymers together to form a structure. And in the rubber manufacturers, they just know to add those kind of fillers, silica or carbon. They don't know, okay, what's the microstructures looks like. So nowadays they may seek help from AFM to say what's the real microstructures looks like. So the AFM images is coming. So we did a topography images, and we did see some bumps. And those bumps show the high modulus. And we know the rubber itself is the polymer should be near gigapascals, and we add the carbon or silicon or silica, it may show higher modulus. So we would guess, okay, maybe those stiff particles, they may serve as a core. And then all the other polymers is correlated to this core, and to form this kind of core shell structures, and to make a network of the inside of the tire. But okay, that's the chemistry, that's the educational guess of our chemist. And then they would ask, okay, what polymers is surrounded these silica particles? So from the modulus itself, we may not be able to identify it. And now with the help of the IR, we can study the IR absorption on those stiff particles. And from that, we see the signature of uracil at 16,058, and it shows a significant absorption here, gives an IR signal. So we can know the structures clearly. This is the silica particles, and it's surrounded not by our polystyrene, but nor the blending, but the erasing. So that's the information of those tile guide they need. They as such they can change the chemistry structures as such to change this core shell structures. So that's benefit their applications. So I would like to stop here and give a brief summary of my topic today. So the AFM is served as an imaging scales. We use the probes to get the morphology first, and then we use the probe to serve the stylus to capture the to measure the mechanical properties such as modulus, such as viscoelasticities of our samples. And then we can get a mapping, we can get a quantitative results. And besides that, we can combine this AFM techniques with other with other techniques to expand the AFM's applications to serve a good tool for your daily research. So we are still explore the possibilities with these techniques, and just like Dr. Chen said, we want to use the small probe to explore big science. And that's my topic today. Thank you.
Thanks for Dr. Liu to share about the mechanical application C, AI, So now it's a Q&A session. So if anyone has questions, just raise your hand.
Or you don't need to raise your hand, just shout it.
Yeah, so if you now, just make sense well the presentation. So next time, I will invite Dr. Xu to have a presentation about how the optical tweezer, the bell air can apply on the bell materials and their applications. Yes.
OK，我们有麦克风，刚才有人用是吧？ Okay, good afternoon, everyone. So it's my honor to give an introduction about our BioFM and optical tweezer system. So my topic today is actually quite biology, because I just want to introduce something about how to use two setups to quantify and manipulate what we call the biological force. And before the discussion, and I just heard from Dr. Shi that, and he don't want you guys to bring the, the biological sample to the icon system due to the risk of the contamination. But a good thing is that actually in other campus of UST in Guangzhou, actually they have a very good, our flagship mode, this the new Nano-Wizard BioFM, and also with a very good confocal system from this. And if you guys want to have a try, maybe connect the BioCF in Guangzhou, and you may get something you want. So here I introduce our products. And first of all, you will see that our flagship BioFM, we call it the Nano-Wizard FM Scenes. But based on this mode, and we also have some specific production lines, just like force robot and the cell adhesion. The upper one is focused on the single molecule for spectroscopy. Basically, people using this product to do the study of the molecule interaction, intramolecule action, something like that. But for the cell adhesion part, people use this product to study the tissue mechanics. Excuse me, tissue mechanics, and most importantly, and people use this product to study the cell adhesion. For example, here we have a cell, and we measure the interaction between the cell and the materials. And besides, we also have other product. just like we have the optical tweezer, and in a way, it's also one technique of the scanning probe microscope, and we also have the ultra speed product line, which is to study to do the fast scanning, or you heard the term of the high speed AFM things. And in the central, we have a unique system, which actually is the optical tweezer combined with our AFM, and we will have an example at the end of the whole presentation. So let's go to the FM first. So for biological study, commonly you apply the FM to do what kind of measurement? So here we have a very short summary, and basically people you study the structure and of the biomaterials and the biosamples, and also people study the force and the molecule force, cell force, and the other thing is that people use the AFM to study the dynamic things. This one I think is kind of unique, because commonly if you are using the electron microscope to study the dynamic things, it's kind of hard. But for AFM, we have some tools to study some molecular dynamics events. So for AFM imaging techniques here, we have the resolution from the lower to 1 nanometer to up to 1 millimeter. So across basically this scale bar across the sample size of all biomaterials or biosamples here. And what kind of imaging we can get here? I mean, from the smaller features, we can use the AFM to see the minor and the major groove of the double string DNA. And here, if you want to study some lipid bilayers, we can use AFM to see their transition and the temperature, just like this imaging. And also, and the people use our AFM to do high resolution of some amino fibers in the left panel, and you can see that we can use the AFM to measure the D shape of some amyloid proteins, and the right two panels, and here you can see that the high resolution imaging of some DNA origami, and this one I think quite hot in the research field, because these materials have the capacity to be some drug carriers things. And except for, besides all these molecules, and also the other thing is that related to the structural biology, because commonly if we want to study the structure of some proteins, we may use the X-ray, and also the most well-known technique is the cryo-EM. But here we use the FM can visualize some membrane protein, commonly membrane protein. And so here on the left side, we can see the BR protein. It's a membrane protein, and it's photosensitive. And on the right, on this red panel here, actually is from a research group in Shandong University. And they just use our Nano-Wizard AFM to visualize a very new protein super complex in the plants. And because this one, you see that it's a photosystem protein and absorb light, and this super new structure people never seen before, but under the AFM, they can see it, and they visualize the structure, and also combine it with cryo-EM, get some new structure things and functional structure. So molecules, and then we go to some bigger particles, the smaller one, and we can use our AFM to see the proteins of the code proteins of some virus, and bigger we have the images of some bacteria, since we see the porous structures on bacteria. And the last one, maybe of the high resolution, is that we can even use our AFM to see some living cells. It's very hard, because commonly, if you want to just use our confocal to see the XZ section of some cell things, it's kind of hard due to the resolution of the optics lens on the Z axis. But by using the AFM, actually, with a relatively low set point force, we can see some microvilli structure. And yeah, maybe in the future, if you want to see some structure, for example, the hair cell, some guys may heard the hair cell, some hair bundle structures in your ear. Maybe you can use the AFM to visualize this tiny structure, see something you haven't seen before. So that's some high resolution images of biosamples, but are you satisfied? Actually, no. So for some people, no. For example, the Professor Toshio Ando in Japan, he was not satisfied with the static images. What he wants to see actually is the dynamic things, because in biological process, we are always talking about some reactions, some protein-protein interactions. I want to see something dynamic, not static things. So here is I think it's a cornerstone publication of the high-speed AFM. And actually, the first time people use the AFM to visualize the myosin 5, which is working on the microfilament, is quite new at that time point. But to this time point, actually, we are using the high-speed AFM. We have another term, the fast scan, to visualize some molecular dynamic things. I have two examples here by using our Nano-Wizard system. The first one is about the amyloid fibers. So people, if in the biological study, may very familiar with this term, because this one is every time we talk about this term, it refer to the neurotoxin. So neurotoxicity, and here in this study, and people want to see whether some protein chaperone system can remove this kind of amyloid fibers. So in the reaction system, they just introduce the 3 protein chaperones, and here you can see the degradation of these amyloid fibers, and well, you see just adding the protein chaperone, you see the whole thing just gone. So the second case is macromolecules, and for these molecules, the property of this one is if under the UV light, the whole shape of this macromolecule is round, but when you shift the light wave, the wavelength of light from the UV to the green light, you will see the irregular shape of the whole molecule. But when we come back to the UV light, the irregular shape will come back to the round shape. And we are using the AFM to see this transition of this surfactant, which is a responsive. So yeah, we have some examples of the imaging part for AFM in bio or molecular material studies, but the main topic today is how to use our AFM to measure the biological force. So why people want to measure the biological force in their study? So we found some motivations, maybe not full motivations for this kind of study. And the first one is that if we just go through our organs in our body, we will see that actually for the stiffness of living tissues, actually in this term, and every time you see the stiffness, commonly used biology study, not in the mechanics study, and the people use it to describe the hardness or something of our organs. And you will see that actually it's quite a wide range, and from the to 1 kilo just to some gigapascal. And so you see that, okay, the range is very wide. Does it mean something? And yeah, the other thing is that if you want to know the term of the stiffness, actually you need some tools to measure it. And here we also mentioned that for some cancer and for the pathological alterations, actually the stiffness of all these tissues will be altered. So mechanics and in the study of this time actually tends to be a biomarker things. And just like what we show here, actually people already found that in the development, just this one, the tissue will just exhibit some special pattern of the stiffness, and in some disease in the center, actually in this case is for cancer. And people find that in the normal tissue and the invasive tissue, you will see a obvious difference of the distribution of the whole tissue stiffness. And in the third part, you will see in this case of regeneration, you just broken the spinal bone of the fish. And when the whole tissue goes through the regeneration, is actually for the tissue part, it will undergo the change of the stiffness. It means something, but for this paper, actually they didn't explore too much of the underlying mechanism. Maybe you guys can find something in this kind of tissue regeneration and the development. So as a tool to study the biomechanics things, our AFM tools, what we can do. The first thing is that we can do the AFM, nano indentation, that's the thing. And for our BioFM system, and then the other thing is that we have a very good combination of the AFM and optics things. We can, which means that we can combine the two signals from two different systems. So for the FM part, so what kind of events we can study? So here, so first thing you can see that the force range in the life science study by the FM is that we from the piconewton to up to maybe dozens of nanonewtons. So for the events, and sometimes we are using our AFM to study the molecular events, and sometimes we just use our probe to study the biomaterials and the stiffness of cells, and sometimes we also study the cell adhesion event. We have some example here. So for the AFM based for spectroscopy, or another term is that AFM nano indentation, and actually we get the force distance curve, and I think you guys are very familiar with it. And in this, so what we can get from the information we can get, so we have the Young's modulus, or sometimes you directly see the term, you have the stiffness of your biosample. That means something. And then the second important term is adhesion. Okay, you have the cell maybe attached to another cell or to some materials, and we can measure it. And then the other thing is that here we also mention here, you can measure some work of the adhesion, or even something more. But that's the whole, basically the whole thing we can get from the force distance curve here. And the other important thing is actually we can get a height single, because the force curve imaging method actually is very good for some living cells and soft materials. And the other thing is that, for people to do the FM study, you need a good probe. And here is actually a recommendation for guys, if you guys want to measure the mechanics of some tissues, cells, so which probe would be good for a study? Here, we have spherical apex probes, and these probes, we have different radius from the 1 micrometers to 5 micrometers, 10 micrometers, depends on the region resolution you want, and we have these options for you. And if you guys want to do study, maybe can think about it. So the typical measuring experiment by the BioFM. So the first one is actually the living cells. So almost every people, if they know that we have a BioFM, so I want to measure some living cell stuff things. So sometimes just we get the stiffness of a whole cell, but here you see that actually with our instrument, we can get a high resolution image of the cell. And here you can see that we have the surface information from the height imaging, and from the pixel difference imaging, we get some more details, just like error signal. And then the lower panels here, we also have the Young's modulus figure. Actually, it's a little bit different from commonly you see in the paper, because this one actually with a very high resolution, and also the pattern of this Young's modulus, we can see it resemble the structure of some cytoskeleton. Just think about some cytoskeleton endless membrane. Yeah, we can get from the AFM images. The second one is actually, this one is a tissue, and the people want to measure the mechanics of tissue because sometimes related to disease, and we may also mention to development. Here, by using our BioFM, and we can do the multi-scan of the whole tissue at different region. And sometimes I think it's very good, especially for someone want to you want to develop a new tool as a diagnostics tools to, for example, you want to test cancer, or you want to test some other disease, and you have the tissue sample, and maybe you can use our BioFM to measure the tissue mechanics things. The information you can get here, we show the Young's modulus, but later I will introduce is that for our instrument, we can also give you some viscoelasticity things. There are some, and in the paper, we commonly just talk about the stiffness. Actually, the Young's modulus, why people want to get this one, we will talk about it later. The third part is a single molecule for spectroscopy. And for this sample, GB1 protein, this one is from Professor Cao Yi. And yeah, from here, you basically you can see that, okay, you can attach the protein you want and do the single molecule for spectroscopy to study, do the study of the intramolecule force. And for this one is just how to dismantle one subunit of the whole protein. Maybe a little bit boring, but later this one may be more applicable is that sometimes just for this one, we know that COVID-19 and the people, everyone want to develop some new drug actually. So the basic mechanism to block the interaction between the S protein and also the receptor of ACE2. So here, in this paper, actually, what they do is that they just coated the S protein on the probe of the AFM, and then on the substrate, you see that they just coated the substrate with the ACE2 receptor. So in here, we can see that. So here we can see that when they apply the ACE2 antibody or just apply some drug, actually it can block the interaction between the S protein and ACE2. So it's just a model case, and maybe in your studies that I found two protein interactions. That's for virus infection, and I want to interrupt this this infection. Maybe we can use this system to find which drug or some special design antibody can just block this interaction. The first part is a single cell for spectroscopy. Just as I mentioned that this one people want to use to make the study of the cell adhesion. So sometimes between cell-cell adhesion, this one is commonly we see in the study of the immunology, because in the immunology, we have maybe T cell, DC cells. We just want to see the interaction because this interaction commonly indicates the binding of some antigen pattern just delivered to a lower cascade, lower cells in the cascade, or sometimes people just want to see the cell adhesion between the cell and the material things. For example, you just develop some antibiotic materials and you want to see whether this material have a good affinity to some bacteria or even to some cells. And just so what you can do is you attach the cells to the cantilever of the AFM, just measure the adhesion force between the cell and the membrane. So maybe you guys already know the icon system. So when we look at the bio-FM, so the major difference between the icon and the FM, the first impression, you may say that, okay, looks like your scanning head is on the microscope. Well, it's not that kind of independent, and the two systems that's integrated together. Yeah, that's the purpose. The purpose here is that we want to get the image just here. We staining the nucleus, DNA, and also staining the affecting system. And so then we just select the region we want to measure, and then we overlay the data from the AFM and also from the fluorescence microscope together to do the in situ measurement or in situ analysis. So for this combination, I mean, the primary purpose is that I just see this. I want to see a sample and the microscope, and then I just select this the sample what the region I see, and I want to do the AFM image just like this one. Well, this is very simple, right? But later we found that, and we can combine with more than just bright field or phase contrast or DIC. We can also combine them with a fluorescence confocal turf here, and even I mean, not in the mainland or Hong Kong, but in Europe, and we have some cases of the combination of AFM with the super resolution, just like storm, STAD, and SIN. So we have two examples here. The first one comes from our factory, and we have a collaboration with Everreal. Every people know that they have a very good STAT system and also mean flux. So, and in this setup, since that we have the combination of the bio-AFM with the STAT, so the whole system is working like this. We have the AFM probe working on the upper surface of the sample, and the lower part we leave to the STAT system. We have the excitation and the detector things, the whole thing together. So for these living cells, we stain it with the microtubule and stain it with the fluorescence dye, and then we select this region to do the FM measurement. We get a high single, and also we have the osmotic single. So not only the inverted microscope, even you have an upper right microscope, we can still combine our system. So here, this publication last year, and there is a group in Japan, actually they combine the same system with our AFM. So here, because they are using the same microscope, same techniques, so the imaging of the fluorescence image is quite clear with a higher resolution compared to the normal microscope. And also for the P0 and adult samples, and actually they can see the pattern there and coordinate the signal from the AFM with the with the SIM. So here, so I just want to say that if you guys, some of you may be very familiar with optical scenes, our AFM is kind of flexible for you to combine two systems. Maybe you can find some new things. So the other thing is that for our things that we see something and we measure it, and for us, we also provide some optical telling and the smart mapping things. That's for the large area tissue mechanics study. So just like one case here, we have quite a lot of cells. So basically, it's kind of hard. You need optical telling to get a whole image of your sample, and you get it. You do the optical telling, and you just you have the automatic we have the automatic selection for you just to select the region you want to, the ROI, and you just select these regions and do the scanning, get the whole signal here. And then the other thing is that we have the smart mapping, and this feature. And the good point of this feature is that actually for the probe, commonly for the scanning, you know that we have a limitation of Z range, and commonly for the BioFM, maybe just you don't have the salvation, you only have maybe 15 micrometer. But with this one, because we let the probe to do the engagement at every point, just like the mapping at every point of the mapping. So, which means you can do the force mapping at a very rough samples, maybe 100, 200 micrometer. You can still do the force mapping. Okay, just like this one. And also you can do the whole thing in a very large range. And we have this slice, very large, the tissue slice, and so you can do the force mapping in a very large range. And for this one, and you also have the immunostaining, and you can coordinate these two signals together here, just like this one. Another good point for this smart mapping feature is that it's kind of flexible. Not only just we are talking about the out of limitation of the range, and the other thing is that actually you can select what you want. So sometimes you have a cell, and you just for the commonly you get a rectangular force mapping, and you said, okay, some part is due to the stiffness of some part is only is due to the substrate. I don't want it, but with the force mapping things, you can draw just on your cell and the region where you want, and you can get the maps just like this one. So the biological force explore the BioFM here, and we maybe have a more detailed case where I have some case from the molecule to tissues. So here, first, I want to mention that why more and more people want to study the biomechanical things. And here, because it's due to the found of some very new mechanical sensors in a biological study. And the first one are people know that because they already have a Nobel Prize. The first one, people found the piezo 1 and piezo 2 channels. And these figures from the Nobel Prize website. And the importance of this channel is that, I think it's the first time every people was convinced that if you applied some force on the tissue or on the cells, these ion channels can be activated, especially in the eukaryotic system. I think it's the first time convinced. And later, after they found this one in the 2010, and some followed publication just like this one, and if they mutate the piezo 2 channels, actually there will be some disease, the abnormal development of your hand and of your bone. There are some patients and to convincing that from the physiological view that the function of the mechanical function of this protein is true. Another famous sensor, I mean, for the study is about this white protein, YAP protein or YAP test modules. This protein is very interesting. Is that at the beginning, people find that okay, if they apply the rigid pillars or have some very stiffer substrate, this protein will just do the translocation from the cytoplasm into the nucleus. So, I mean, for this new for sensors, I mean, previous people more study about maybe focal adhesion, cell skeleton sensors, but after people found these sensors, people found that maybe we should pay more attention to the biological force involved bioprocess. So what we can do with our BioFM to explore these molecules, I have 3 cases here. The first one is that, I mean, for the piezo 1 and piezo 2, piezo 1 and piezo 2 proteins, actually, this case people want to resolve that. If we see actually they have the for the whole system, they have the AFM and then they have the calcium image, and they want to see that whether only piezo 1 or piezo 2 or piezo 1 plus piezo 2 will be responsible for the calcium influx. So by using this system, we use the AFM cantilever to press cell and see under which condition there would be a calcium influx. And actually, in this paper, they just found that if you co-express the piezo 1 and the piezo 2 together, there would be a calcium influx, which is very important for the downstream signaling. And the second case here, sorry. So here is that I mentioned the YAP protein. This protein under force will do the translocation from the cytoplasm to the nucleus. And for this study, they just use the AFM probe to touch the different region of the cell. The first one, they just touch the nuclear part, and they can see the protein just translocate from the cytoplasm into the nucleus. And then the second one, they just touch the cytoplasm part, and the protein will not do the translocation. So the question rises up here, because we know that there is a linkage between the nucleus and the cytoskeleton system. So whether the force is from the cytoskeleton to a nucleus or nucleus itself serves as a mechanical sensor. So they use the very classic inhibitor cytokinin D just to destroy the whole cytoskeleton structure and press the nuclear part. And even with under this struct treatment, they can still see the protein, YAP protein will do the translocation from the plasma to the nucleus. And then the third one is that some protein, this one is actually SAC protein activation. And here is that we can use the AFM chip just to stretch the collagen of the collagen very close to the cell. We apply the force and we use the fluorescence microscope and to see the sensor. And by this way, actually we can just see how the force activate the SAC protein here. So so here are 3 examples of molecular modulations by the AFM probes. Then commonly people will do some cell force measurement. Here, just the first case is that for here we use the AFM cantilever to trap one cell, but this cell will undergo the mitotic process, and in the whole process we can see there are force. But what's the meaning of this force? And we see some force difference change here, and the new published paper here. Just this year, actually people find that the force of the nucleus can serve as some checkpoint for the cell cycle, here. The major mechanical unlike difference is that they stain the laminin proteins and on the nuclear envelope, and actually you can see that for the normal cell or just treated which induce the segregation of the of missegregation of the chromosome, and you will see the laminin protein actually features this one just like a line, but for this one, you will see a lot of curvature inside, and which means some abnormal structure. But when we use the AFM to measure the stiffness of the nucleus, actually, they can see that, okay, for the missegregation part and missegregation cells, actually their cell nucleus stiffness will drop dramatically. So here, and even here, this case, I also found this paper of this year is that people found for cancer cells, sometimes, and I think it's the first time some people refer to the cancer cell mechanical competition. The basic information here, the whole background information here, you see that, and for some cancer cells, if you don't apply some compression, here you have 1 and 2, and you apply just some compression here, for some cancer cells, they just die out. But for these kind of seeded cancer cells, if you apply the compression, actually the cell will, it still grow well. So what's the underlying mechanism? So they found the signaling pathway here. So you find that for the die-out cells, actually, there is a signaling pathway actually through this signaling pathway, and finally myosin-2 activation, which will induce some apoptosis of the cell, the death of some cell. But for these mechanical resistance, which win the competition cells, actually they have a signaling pathway comes from the category download, you see 1, 2, 3, 4, 5. And they confirm the whole thing by what? Just lock out or lock down or introduce the inhibitor of these proteins. Because basically, I think the reason they don't do knockout is because they are lethal. If you totally lock out, but if just lock down and also introduce the inhibitor, and basically you will see an increase of these Young's modulus of cell stiffness, which convince that, okay, the reason why these cells can win this mechanical competition because they have this unique signaling pathway activation. But here, so for all these numbers, you see quite a lot of those. And for every biological replicates, they need 70 at least 70 cells. So maybe not large enough, but for AFM, work is kind of labor intensive, and too many cells, right? If you have money, maybe you can have this one. So we have a cell wizard system. So you see that we have a four well cells, and we have cells inside, and we can do some automatic test. So the whole thing is based on, and this one, I think it's open source software, is that maybe some people know that we have a cell pulse. And the whole thing is that we have the cell pulse and to recognize some special pattern cells. And our system can, based on the AI data pattern and collection, and to select the cells in your samples, and okay, just do the whole measurement automatically. And maybe it's very good for you to do this kind of study, and in a much easier way, make your life easier. And the other thing is about the tissue pathological samples here. So here I have some disease-related case. The first one is about heart, and for ischemic injury of the heart and the loss of the blood things, and it will introduce some scar on your heart. And the thing is that for some patients, actually the scar will will decrease the stiffness of your tissue. And here, people want to study which collagen is involved in this scar events, and they found the collagen 5, and they measure the stiffness of tissue between the control and the collagen 5A1 condition lockout, and they can see some 15 degree decrease. And so to confirm that, okay, the collagen 5 determines the mechanical property of your scar after the injury. The second one is the infection. So we have the pylori infection in the pediatric patients, and so they have just this infection, and people get a sample, and they measure the the stiffness of your stomach tissues compared between the healthy patient and the infected patients. So basically, you can see a dramatic decrease of the sample. The third one is a plant case, and because people find that okay in the wild, they just find some irregular branched birch trees, and so the very basic hypothesis is that okay, it's due to some mechanical strength laws of the plant, and then they can just do the section, get the section of the plant and do the AFM measurement, and then they find some new mutation loci of this birch tree. And for the studies in the past years, people pay quite a lot of attention to the tumors. The reason, just like this figure here, is that because for the tumor cells, actually, one important thing is about the microenvironment of the tumor cells. And for people study the biochemistry, you may find some chemical clues. But here, some guys just pay attention to the mechanical stuff of the tumors, and in this paper, actually, they found that why some T cells, just CD8 plus T cells, just exhausted in the tissues. And the major reason is that they found a mechanical pathway. Because, and here in this paper, they just, maybe you are interested, you can look into this paper, is that okay, in some region of this of the tumor section, and they just measure stiffness with the high level collagen 1 level tissues, and they found that okay, the high level collagen 1 tissues, no matter, I mean, the stiffness of these tissues is quite high, but the important thing is that they found some T cell exhaustion markers, well, it's in quite a good correlation with the stiffness of the tissue, and that's the cornerstone of the whole study. And then they found a signaling pathway. They found that piezo1 serves as a sensor to make the T cell to feel the stiffness of the whole tissue, and then just they find which finally they found this OSR2. I don't know whether some guy involved in the study of development. Actually, this one is just for the bone development. It's quite new, and some people told me that it's surprising. Okay, maybe this one is the last case of the tissue things, is that for this paper published last year, and from the Christopher Chen, and he want to study the metastasis process of cancer cell. For here, they want to see the infiltration of cancer cells from the upper layer to a lower layer. So they found the whole story he found, maybe I may directly go to here, is that he found that for the key point for the cancer cells, just from the top layer to lower layer, from the top layer to infiltrated into a lower layer. The major point is the stiff difference between the vasculature structures and all the very soft, the brain tissue part. So the two parts, if the stiff difference is quite large, and it will increase the infiltration. And in this paper, actually, the very brilliant idea is that just perfuse the vascular part just with the here, just like this one, they fill this part with the dextran material gel, some gel, and they have the stiff, and then they also have the soft one. They compare the infiltration of the tumor cells, and they finally find that okay, that's the stiff difference of the whole thing just trigger this process. So maybe last part I'm talking about here is that people are more than just study the stiffness things, because for stiffness, people already use the AFM to measure the whole thing for maybe decades. And now they found some new terms to play with, is the rheology. So what kind of the origins of the rheology? Here, I found two sources. The first one, just we look at the tissue things that is related to the cell density. So three conditions. The first one is due to the cell density, because some part during the development, and sometimes due to the wood hearing, and the density of the cell is quite different. It will introduce some rheology difference. The second one is the cell-cell contact formation, and the third part is the cell motion. And no matter which conditions, it will cause some rheology change in the tissue, and it will trigger something happen, but not many people study yet. And another case, actually, this published paper is about the viscosity of some tumor cells. And for this one, it's related to the advanced glycation endpoints of the ECM. The ECM actually basically is that the structure and the substance change actually caused the substance structure change caused which introduced the viscosity difference between different samples here. So here, actually, if we just directly look at the force distance curve, you will see some shape difference there, right? But for this paper, they don't use our tools, but they use the rheology meters to measure the rheology property of the tissues. For the stiffness part, they don't see any difference, but for the rheology part, actually, they can see something different. So for our system now, we have the cell map package, and the basic for this system, we just use the AFM probe to touch the surface of the sample, and we introduce some periodic deformation, which causes the periodic force of the stress between the probe and our sample. So we have these features, and just maybe we'll directly go to one sample here. We have the spheroids, some protein, some cells just cell clouds, or some cells just grew together, and we use our probe to measure. So just for this example here, and you can see that at a different part of all these cells, actually, there are some difference in the viscoelasticity here. And then for our system here, we can even give you some high resolution maps of the storage modules and loss modules things. And if you want to try, and maybe can try our system. And so here is a short summary just for the FM part, is that for FM part, and people want to see more dynamic things, and we use force in the study of cells, tissues, and biomaterial things. And our study includes biomedical and some basic research. Yeah, that's the whole thing for the FM part. Then let me spare some time for our nano-tracker, our optical tweezer system. It's kind of different. I don't know, maybe some of you have already used this system before. So here I may make the whole thing simple, is that, so for our system, we use a very high NA objectives to trap some particles. So the range of the particle, the size of particles we can trap is from maybe the lower to 25 or 20 nanometer up to maybe 115 micrometers. And so the whole thing is quite like, the whole system is quite like AFM. We are using the same law to see the force on the trap. And we have, so for this one, we have the detector here, and we measure the force in the XY plane. But the different thing is that for AFM, we just measure the vertical force, and for this one, we have the XY, and also we can measure the force on the vertical, and have the detector to measure the force, and also the position of our particle. So the study we are doing that here. So compare the optical tweezer with AFM, you will see that the optical tweezer, the force range is much lower, and we have a higher force resolution, maybe up to 0.1 piconewton, and the force range is from the maybe around 1 piconewton to just 1 nanonewton. If we want to use optical tweezer to measure, for example, cell adhesion, but at a range of would be several newtons, maybe better use the AFM. But for the whole study aspects, we studied the molecule things, and we also studied the cell mechanical stuff. So some examples, the first one is a cohesion protein. This protein will serve the function to separate the chromosome during the mitotic, some cell cycle things. But here, by using our optical tweezer, is that we can link the protein we are interested to the base, and then we just like this figure, like this video here, we just pull this, actually here when we pull the stage, and we can see at which force and whole protein will detach from the DNA here. The second one is that, and sometimes we also use optical tweezer to measure some states, the states of some protein here. So for this protein is have some different state, just like my elbow and fully extended or have 90 degree like this or fully folded. So by using the optical tweezer, we can link our molecules to the beads, and we just measure the force. And kind of like I don't know whether you guys seen the data from Patchcam is there are three states. So with 0.5 piconewton, 1 and 1.5, which indicates different states of the protein. So for our system, a feature of our system is actually we have some multiplexing. So make the whole thing simple is that we have one beam, we have one trap, but we can separate it into up to maybe 200. Well, just for the manipulation, sometimes no more than just 20, and which means actually we can use one trap to trap quite several beads, just like this one. So this one is the trapping the beads of the DNA, and just do the trapping movement. And for this panel, lower panels, we have 4 traps. We just do the dragging things, and we measure some viscoelasticity or something here. And one application case here for this feature. And sometimes if you want to study the interaction between one filament and another filament, how to do this experiment. So here we have the multi-traps. So we have the multi-trap, we have 4 traps, just we separate one trap into 4 traps, and we use 2 traps. Just like here, we trap one filament, and we use another pair of the trap to trap another filament, and we just make the interaction and see the detached force of the whole event, just like this. So besides these molecule events, we can also measure the things that for the optical tweezer is that we measure some living cell mechanical things. So for our system, we think they are good. The example here is that even in the zebrafish, it's a living creatures, and we can manipulate no matter the particle or cells inside the zebrafish. So it's good. And so the other measurements we can do by using the optical tweezer is that one is that we can use optical tweezer also do the nano indentation. So the major difference between the AFM is that AFM we do it in this direction, but for AFM sometimes people say I just want to see the modulus property in the XY plane, and so if you want to do this kind of experiment, we just use our optical tweezer to trap the beads and to do the indentation of the cells. And also we can measure the tether force of the membrane, because just like the piezo 1 is the activation of the piezo 1 is determined by the tether force of the membrane. Sometimes people want to get this property. So here for this experiment is that you have the sphere and you make a contact with the cells, and you just record the nano indentation process and fitting the data to the model, and you get the tether force of the system. And for this one is that you can do some rheology measurement inside the whole thing. Here we have some data is that because for some solution, and for solution you have some macromolecules inside, so the viscoelasticity is quite different from just with PBS solution. And do this experiment, you just trap the beads inside this bio solution, and you do the dragging experiment and fitting into the models. So this one maybe, and the crazy experiment I heard is that people actually do this experiment in the concrete, which we just pave the road. So which means because inside if you want to study the inner viscoelasticity property of the concrete inside, you just manipulate the beads inside the concrete and do this kind of measurement. Yeah. And for the cell things, and sometimes you will just measure some special special structures. And for this one, because there are some nanotubes between cells, and we can use one bead just to steering the nanotube structures, and because there are double or single nanotube bridge, and we use this method to can measure the stiffness of this nanotube. And for this one, we have a customer in mainland, and they are using our optical tweezer to study the flagella of some bacterial motion. The whole system is that we can use optical tweezer because we have at least 2 traps to trap the bacteria. To don't make it, because you have one single trap here, you trap a bacteria. What's the motion of the bacteria? Yeah, it's on this position, but the bacteria will just rotation like this. But for this kind of study, they just want to, okay, the motion I want is no rotation like this. I don't want this rotation. So they just apply the 2 traps to trap the bacteria, and they use the high speed, they use the high speed camera to monitoring the motion of the flagella, and they just analyze, for example, this part, and see the power spectral signal. They can see the frequency of this rotation. And for the whole purpose to establish this system is that, okay, they use the optical tweezer to trap the bacteria and put the bacteria under different solution. One maybe only solution PBS, the intro, they just introduce high concentration of some sugar things, and they want to see and a different viscosity, and they want to see and different viscosity what's the motion of the flagella. That's right. That's the whole experiment. So now the last part of my introduction, actually we have the optical tweezer AFM binding system here. So we call it the OTFM. So the main point is that, and we have a system, and sometimes the optical tweezer can only be used for the manipulation, but actually we have a system. We can use 2 systems independently, or we can use them together to do some experiment. And here, so in this system, you have maybe more than one, more than one probes. You have the probes of AFM, also you have the traps from the optical tweezer. So what kind of experiment you can do here? So we directly go to this case. So for this one, they have 3 cells. One is the Treg cells, this one, and then the second one is the DC cells here, and the third one is the TC convolutional cell here. So the whole immune story is like this. When T regulatory cells combine with DC cells, and actually it will suppress the immune response of DC cells. And in this case, is that which is the T conventional cells, in fact, the adhesion force between the T conventional cells and these cells will decrease. So for the whole experiment, they just use the optical tweezer to trap the T regulatory cells and make a connection between the DC cells. And then at the same time, they just measure, okay, what's the adhesion force between the T conventional cell and DC cell? They can see a dramatic decrease here. And then they just move the T regulatory cells away from the DC cells, and they measure the adhesion force again. It will come back. Yeah, just like this system. And this one is quite unique, I think. Yeah, in the future, if you want to do this experiment, yeah, just try it. So a short summary for our optical tweezer part is that, I mean, a little bit different from AFM is that we can do the 3D manipulation things, and we can measure the force, quantitative force measurement. And for our system, and the major difference from other systems is that we can combine with quite a lot. We have a flexibility to combine with different brands, the mainstream microscope, and you can combine with the fluorescence, confocal turf, and the Raman, and all of them. So maybe that's the end of the whole things. So any questions? Okay, maybe we can have a discussion later, and yeah, we have a briefing. Yeah.
So we have some cakes and other so that's all. I'll maybe come back after 20 minutes.
So.
OK，
好像没有抓到那个怎么说？
在这个今天的这个
对对对。
但是他的名下为主哦，那张老师
可以，我待会儿这样给你切过去。 Oh, okay, everyone, let's go back to the seminar. So that's what the Dr. Wu Ren, they will have a presentation about in the semiconductor industry, how to achieve the nanomechanical measurement. Yeah.
Okay, thank you for the introduction. And my name is Wei. I'm very glad to have the opportunity today for sharing some experiments about nano indentation testing for semiconductor. So, sorry. Yeah. And actually, we have two. We are a mechanical metrology tools, and we actually have two product lines. One is the one, which is a standalone system designed for testing samples in the atmosphere and environment. And the other one is the one, which is a we call a pico indenter, which is designed to be an atom for electron microscopes. For example, that is the one you can see it is the size that is, and you can put the whole things into your SEM. And then we are able to perform some indentation tests within an SEM, and even though TM. So the good thing that we have is we can have the mechanical data together with the synchronized SEM video, and sometimes they will be very powerful and very helpful for us. And at very beginning, I would like to make a very brief background introduction about semiconductor. Actually, all of our cases today will be are actually related to semiconductor applications. So this is some failure cases happened in semiconductor industry or products. So you can see actually they are mainly the cases of delamination. So we will spend some time and some cases talking about cracking happened with two different materials, so-called interfacial debonding, which are quite significant, I would say, quite significant to semiconductor products or engineerings, because you can imagine that nowadays we actually have a lot of layers in our microchip or semiconductor products. So the number of interfaces is actually very huge. So we don't want something like this happen in our device that will be a disaster to our application. Okay, so very firstly, I will spend some time talking about, actually we have two main topics today. One is talking about the intrinsic mechanical properties. That means we are focusing on the mechanical properties of one single layer itself. And the other thing is for interface, which is a some kind, you can imagine that it is a kind of interaction between two different materials. So we'll have these two different topics. So very first one is for the intrinsic properties. So we are focusing on only one single material. Typically they are thin things, and we would like to categorize the mechanical properties, including the elasticity, so-called modulus, which is the index about how deformation, elastic deformation happened to your materials. The other one is the plasticity, which is so-called the hardness or strength. And yeah, for our basic indentation idea, one single indentation test can provide two mechanical properties, a set of two mechanical properties. One is plasticity, which is hardness. The other one is elasticity, which is modulus. So this is the basic idea. One test, one indentation provides two mechanical properties. And for the third one, I would like to skip this one instead of discussion of interfacial debonding. So not really a fractal toughness, but it is also the idea about resistance to cracking. But the cracking have the cracking is happened between two different materials. For example, this is maybe the top layer, and the other one is the sub layer. So this phenomena we call delamination or interfacial debonding. So that will be our second topic. Okay, so I would like to give you a very brief introduction about nano indentation. So I'm so sorry that this video cannot work properly here, but I would like to just briefly give you a very simple idea for performing one single nano indentation. We are actually using a sharp tip with a well-calibrated geometry, and we record the force applied into the indenter of the probe, and the probe, another sensor will record the displacement, which is the penetration depth go into that sample. So we will typically have two different segments. One is so-called loading segment. The other one is unloading segment. So if there is some plastic deformation, you will have non-overlap this loading and unloading curves. And going through some analysis, we are able to convert the force, applied force versus penetration displacement into two mechanical properties, just that I mentioned previous. One is modulus for elasticity. The other one is hardness for plasticity. And the other one is scratch, that we are able to have 2D transducer. You can see that. And we are able to move the probe laterally when a normal force, a vertical force is applied. And the main purpose for scratch testing is to delaminate the interface. So this is the commonly used metrology for a lot of semiconductor industrial to characterize interface stress. Okay. So this is the instrument. So for lab, we are always using this one. So this is a non-automatic tester. That means you can see this. There is a gate, and all the sensors and the probes and sample are installed here. So every time you need to change another specimen, you need to open the gate and uninstall one sample and then put into another sample. So it is manually exchange your sample. But actually, for a lot of applications performed in semiconductor industries, they are actually using this kind of fully automatic machine. So we can see it is I was a very similar one to this one. but two additional parts are designed for this automatic one. So this is the robot. So you can see that very clear, but I can demonstrate to you. So there is a robot and with two gates, and this is low port. So typically there is another transport system overhead. I mean, in the factory, in the clean room, and then transmission system will lay down a box we call FOUP, FOUP, which is a container for a lot of wafers, and then they will land here, and these gates will open the back door of the FOUP, and the robot will go to the specific slot to pick up the wafer for ready for testing, and then open these gates. So the robot will pick up this wafer from FOUP here and then put into the stage. So this portion is exactly the same as this, but just fully automatic and testing. And after all testing is finished, again, the robot will go into the stage and pick up the wafer back to the original slot, and repeat it again and again. And this is specific for R&D. So it's a mechanical, I would say a nano indentation tester designed for SEM. Okay, so in semiconductor scopes, I will say we can see our applications, our tools spreading in a lot of different scope, different companies. So I will say today I will focusing on some scopes. One is this one, so for film delamination, and the other one is for here, for the intrinsic mechanical properties of thin film, especially for ultra thin films, which is the most challenging applications for nano intelligence today. So so this is the outlines, and you can see that only one is for indentation, and the other three are only one is for the intrinsic mechanical properties, and other three are focusing on interfacial debonding. Okay, so our main material shown here is actually low K. So I would like to spend some time here for introduction of low K. So the K means dielectric constant. So it is not really K, I would say, but a lot of people, a lot of engineers will call K. But to me, it should be kappa. I mean, originally. But it means a thin film, typically a thin film or a material which that has very low dielectric constant. And this kind of material or this kind of thin film is treated as a insulator for semiconductor. So they are not conductive at all. So nowadays, the main structure for low K thin films applied in current semiconductor industrial is actually porous materials. So the key point, I would say the key point is how to control the porosity of low K thin films. And the thing is that the tendency is if you increase the porosity, the K, I mean the dielectric constant can go down, and this is a good thing for a lot of electrical applications. But in the viewpoint of mechanical properties, high parameters always means some failure, including lower mechanical properties and lower interfacial bonding strength. So it is like something like a trade-off. You want to lower the dielectric constant, but you don't want the mechanical properties going down too much. So it is the main challenge point. And the other one, the next one, I will talk about polymer top layer, which is quite thick, and the sub layer is copper. But the special thing is we will talking about the environmental control of temperature. So we will debunk the interface at different temperature levels. Okay, so the first thing I would like to introduce to you is the main challenge of characterize the intrinsic mechanical properties of thin film. The challenge is here. So when we apply a force via an indenter and make some penetration depth, we are actually making a deformation area, or you can imagine it is a deformation volume. And if we apply the higher and higher force and the penetration goes deeper and deeper, you can imagine that the deformation area will get bigger and bigger. So if the deformation area or deformation volume is larger than the thin film itself, then some deformation actually is coming from not only the top layer, but also from the substrate or the sublayer. So this behavior is so-called substrate film. So the key behavior that you will have if you make a deeper and deeper indentation, no matter the hardness or the modulus will not stable. I mean, they will change with penetration depth, because you will get more and more contribution of mechanical property from the substrate when you go in deeper and deeper. So that is the idea. So you can see these two very typical examples. So if you're looking at hardness changing with indentation depth, if your top layer has a higher hardness, I mean compared to your substrate, then if you go deeper and deeper, you will find your hardness is decreasing. And this is another opposite cases. So if you look at modulus changing with depth, and you have this behavior, that means your top layer has a smaller modulus compared with substrate. So another interesting thing is this changing behavior is actually highly sensitive to your film thickness. So you can see this very typical behavior. If your film thickness is higher, I mean, if you have a thicker film, you will find the changing, I mean, the no matter modulus or hardness changing with contact depth is not so fast. But if you, however, if your film thickness is very thin, the changing is very dramatic. So it's also relative to the film thickness. So some researchers are doing a understanding for the effect of substrate in the viewpoint of film thickness. You will have this kind of, we so-called the normalized substrate effect. So if you use your indentation depth divided by the fin thickness, and you will find a very interesting behavior that all of these transition curve will go together, will unified, no matter your fin thickness is higher or lower. So it is the I will say the rule, the source research for the rule of 10%, we so-called 10% rule. That seems you can see this transition behavior. Actually, there are two stable regions. One is here, it's a shallow depth region. The other one is here at a deep penetration region. So obviously for this one, it is the intrinsic mechanical property of your top layer, because at this smaller penetration region, your deformation volume is limited, is smaller than your top layer. So you are able to get a stable mechanical property, which is the intrinsic or the pure mechanical property of your top layer. So you can see the border of this stable region is around 10%. So that is we so-called, if you want to use nano indentation to get the pure mechanical properties of your top layer only, the key point is you need to make a shallow depth indentation. How shallow? 10% of your thickness, of top layer thickness. For example, if you were, your top layer have the thickness of 1.2 microns, that means if you can make an indentation with depth smaller than 120 nanometers, then you will go into this stable region. So you are able to get a intrinsic mechanical properties. On the other hand, if you go very, very deep and your deformation volume is so big, so the deformation is almost 100% coming from the sublayer or the substrate, you will have another stable region, which are the intrinsic property of your sublayer or your substrate. So the boundary is not so important, but I would like to emphasize here. So another stable region is starting from 200% of your fin thickness. So it's 10% and the 200%. So, but for most of the cases, most of the applications, we are focusing on top layer. So we are always following the so-called 10% rule. So you can imagine that if your fin thickness is going down, because you can imagine that all the semiconductor industrial is downsizing. So your fin thickness is always going down. So your 10% region will be shallower and shallower, and to mechanical property, to nano-mechanical, nano-indentation metrology, it will be more and more challenging. So yeah, so this is the case. This is the idea of so-called 10% rule. So I have these two typical cases for you. So you can see that for these two cases, the substrate is exactly the same. And we have a very thin and very hard top layer. So we have the hardness strategy with depth like this. So you can see the hardness decreases very dramatically when the contact depth is going up. And this is a modulus, similar behavior. And another case is a thick and softer top layer on exactly the same substrate. So the behavior is here. So it's totally opposite behavior, and the tendency is not so fast because your fin thickness is higher. So this is the idea. So the key point is always how shallow we can get, and it is sometimes how good our tools are. So so I would like to introduce you this one. So now today we have this we so-called mass transducer, which is a mass structure together with a diamond probe together. And then nowadays the product name is X probe. So we are able to perform a very low noise indentation test, which are, I mean, this kind of indentation tester are actually closer to an FM based indentation tester. So this is a example of this one, HOPG, and then you can see we have a loading curve. It's very similar to the force curve of FM application. So we have the diffraction and the approaching curve. So because the deformation is exactly elastic, so you can see they are quite overlay to each other, and yeah, and it is I would say this this data are only achieved when the noise level is very small. So the key point will be the noise. So how shallow indentation depth we are able to achieve depends on how low noise we are able to go. So this is the comparison of two transducers. This is the data collected from our standard transducer, and on the left hand side is the data coming from an X probe. So you can see this is the y-axis is the force with exactly the same range. So you can see this is the noise for a standard transducer, which is much larger than X probe. That is the main reason, the key reason that we are able to make a very shallow indentation, and it is the key point for characterization of a intrinsic mechanical properties of an ultra thin film. So I would like to give you a very interesting example. Again, the x-axis is the dimensionless depth, which is the penetration depth divided by fin thickness. So we are able to have this one. So you can see there are 1, 2, 3, 4, 5, 6 different thickness of low K top there. So the thickness one is around 700 nanometers, and the smallest one is only the fin thickness is only 15 nanometers. So if you still remember, if we are able to, if we are going to apply the 10% rule, that means we need to collect the mechanical property data at the penetration depth smaller than 1.5 nanometer. Which is very challenging. So if you have the normalized or diminished indentation depth, you will find the thinness thing have the range here. So we are, we have large challenging to collect data here. But if you take a look at another cases of the thickest film, you can see the range is here. So this is the 15 nanometers. This is around 700 nanometers. So the range is very different. And you can see that for the thickness of around 700 nanometers, it is very easy to get a stable region because the 10% rule is not so difficult to achieve. We are able to have for example, 69, 65 nanometers data shown here, a lot of data here. So we are able to get the intrinsic property of modulus for this locate to be around maybe around 20 gigapascal. But for the ultra thin film of thickness of 20 nanometers, it is very difficult. You will have very big challenge to pick up the stable region of data if your film thickness is going down to a very small one. So it is, I would say, this is the main challenging for nano indentation applications in semiconductor industrial. This is not a very, I would say it's quite a straightforward issue because downsizing. So film thickness is going down, then yeah, we need to chasing or need to always go down to a shallower and shallower depths. And yeah, it's not easy thing to do. So today, yeah, we have the mass transducer to provide a super low noise to make the data acquisition at super shallow indentation depths possible today. So this is the very first portion I would like to share to you is about the intrinsic mechanical properties collecting using our nano indentation. I think we can, because I'm the last one, so I would like to encourage all of you to ask questions if you want to. I mean, you can interrupt me at any point. I guess we don't need to have a additional Q&A section. So yeah, just yeah, interrupt me if you have any question at any point. Okay. So the second one is about the interfacial bonding. So I would like to give you again an introduction about how to measure or how to categorize interfacial bonding. So this is the overview of almost all kind of ideas of all kind of metrologies for interfacial bonding. Yeah, so you can see that among these 8 metrologies, you can find the common point is to apply an additional external force to debonding or to delaminate the top layer from the substrate and record the required force. So that is the idea. No matter you can see this is the we call bullet method or tap method, 3-point or 4-point method. And this is these are 2 methods I would like to introduce you using our instrument, which is the indentation method and the scratch method. Because these 2 metrologies have 2 important advantages. One is direct measurement, which means you don't need to prepare your sample, I mean, spatially or specifically. For example, for a bullet method, typically you need to find a delimited area at the edge, and the delimitation gap need to large enough. I mean, large enough for you to put a knife into the debonding area. So that will be the key point. And for 3-point or 4-point method, you need to cut your sample into the specific size and specific geometry for the machine of 3-point bending. And yeah, and no mention this one. This one I would say is the most challenging one. We call the back hole method. You need to drill a hole from the substrate from the backside And you need to be very careful not to damage the interface. And you input or insert a certain pressure to delaminate the interface. So it is very difficult thing to do, I would say. So for indentation method and scratch method, you don't need to prepare your sample. I mean, for a typical wafer form, you can put your wafer and we apply our probe directly onto your top layer to induce the interfacial debonding. So that is the very first advantage, direct measurement. The other one is high spatial resolution. So you can see a typical scratch test has a length of maybe 7 microns. That means your delamination has a very small size, and your result actually indicates a highly localized delamination. That means you have a very high resolution. For example, if we have a delamination just in the size of a micron or several microns, you can imagine that for a 12-inch wafer, you can perform a lot of scratches all over your wafer, for example, and you can see the distribution of your interfacial bonding. This is a real example of data set, which is the scratch result mapping. If my memories are correct, it is created according to 1,000, more than 1,000 scratch all over the one single wafer. The interesting thing is you can see the uniformity of your interfacial bonding is very bad. So you have a very strong interfacial bonding on this half, and a very weak interfacial bonding on another edge region. So it is the second, I would say the second main advantage that we can have when we apply the indentation method or scratch method, which is the high resolution. Okay, so I would like to play a video for you. Okay, so it is telling you how a scratch to induce a interfacial debonding. So this is the video recorded in SEM. So obviously this is perform a in situ as SEM scratch. So the top there you can see that we have the mechanical data together with the synchronized SEM video. So that is what I mentioned the previous. Using this kind of in situ tools, you are able to have this synchronized information, and in some cases, it is very helpful. For example, if you look at the natural force, which are the blue dots, and you will find there are actually two different behavior of I would say cracking. The first one is this two small one. Actually, they are actually the cracking happen within the top layer itself. So it is we so-called the cohesion, which are the cracking events happen only in the top layer only. So it is not the interfacial debonding. And this one, this big one, the non-bigger one, are the events are related to adhesion. So it is the real interfacial debonding that we are looking for. So we can see this is the first one when the interfacial debonding happened, the top layer will vanish very suddenly. And yeah, this is the other one. So we can take a look at. Yeah, sorry. So I would like to emphasize, just to focus on the very first two small events. So the cohesion events has the radio cracking. Yeah, you can see on the top there, which means the cracking happened with the top there only. And after that, we have the delamination, which is the interfacial debonding. And yeah, another one. So you can imagine that if you don't have this one, if you are performing a standalone scratch test, you don't have the synchronized SM video, you only have this one, then you need to guess, I would say. You need to guess, okay, this is too smaller one, its cohesion events happen first, and then the very big one is the really adhesion events, which is the interfacial debonding that we are looking for. But with this one, yeah, everything is so clear and so easy to understand. So for a standalone system, typically we have this very similar case, but one thing that we can do is to perform the topography measurement we call posted image. And again, you can see some cohesive cracking on the top there. And yeah, I mean, which is helpful for you to judge these two small one are cohesive event happen before adhesion events. Okay, so this is the first thing about the scratch-induced delamination. So we are pick up this point to get the index of the we so-called critical load, which is the required force to debond the interface. And we pick up this critical load as an index for the interfacial bonding. So this is for the scratch-induced delamination. And the other one is the indentation-induced delamination. So we only perform the vertical loading. And again, you can see the for locate, the locate top there itself is quite fragile. So actually we induce the cohesion events again first, and then some interfacial debonding happen. And yeah, this top there vanished very suddenly. And again, if you don't have the synchronized SEM video, only thing you can do is to make some checkpoint to get the post topography measurement to help us for the judgment of cohesion. Again, we can pick up these critical load to be an index of interfacial bonding, which is the required force to delaminate the interface. So this is the indentation-induced delamination. So we have two methods or two metrologies for interfacial bonding measurements. One is indentation, the other one is scratch. And for a lot of cases, these two different metrologies can have very good linear or proportional behavior between them. So you can see this is the, we have four different interfaces from the strong to weak. Sorry, from strong to weak. And yeah, we applied the indentation to induce the delamination and pick up the critical force for the indentation method. Another thing is we are also able to perform scratch test and then yeah, pick up the critical load. And you can see that for these four cases, for interfaces, no matter indentation method or scratch method, the strong one, I mean, if your interface is strong, the critical load collected from indentation will be higher, will be highest. And yeah, similar behavior will happen in scratch test. And just like I said, for a lot of cases, you will find they are, I mean, these two data set of a critical load are proportional to each other. That means, for example, the proportion here for this case is around 10 times. That means if you have a data sets of your interfacial bonding monitoring using scratch test, for example, one day you would like to apply indentation test, then you don't have to, you know, I mean, give up all the big data before, because you can have a proportional testing like this. You can select a strong interface, weak interface, and then perform indentation test together with scratch test. Then you will find the proportion, and then you can convert all the big data of scratch test into the indentation test. I choose to be told, I would like to tell you a story, true story. In a lot of semiconductor quality control segment, when they would like to change a probe, not only for another metrology, when they decide to change a probe, they will perform this kind of they call the calibration testing. For example, this is the probe 1, the critical load of scratch using the probe 1, and this is maybe the data set collecting from the probe B. And because these two probes has slightly different geometries, and believe me, the critical load is highly sensitive to your probe sharpness. So when they, I mean, decide to change a probe, they will do a thing like this, and they will pick up the proportion between these two probes. Then they are able to, you know, convert the big data in the old time to the new time. I mean, when they are using a new probe. So it is a, I would say, interesting behavior I would like to share to you. So it is a proportion correlation for two metrologies or two different probes. And yeah, compared to scratch test, indentation test has another two key advantage I would like to share to you. One is nowadays our instruments are able to perform indentation test in array at very high speed. So we call high speed indentation test. So in this viewpoint, you are able to induce a lot of interfacial debonding highly locally at a very high speed. So we can see there are total 1, 2, 3, 4, 5. So there are 5 by 5 array of indentation induced delamination, and you can pick up the critical load here. So if we still remember, in this case, we know that these two small events are cohesion. So it is not we are looking for, and this one is the adhesion events. So we can pick up the critical load here. So we are able to have the statistic viewpoint. So because we have totally 25 critical loads, so we have the average value together with the standard deviation like this. And this is the very first advantage of indentation induced delamination. It's high speed, and the other one is high temperature. Because our high temperature stage is designed like this, so you can see that we have the two heaters working together. Top heater is designed to contact with the top layer of your substrate, of your sample. And we have another bottom heater designed for heating your bottom layer. And this design have a lot of advantage. One key point I would like to emphasize here is the temperature uniformity, because we will set exactly the same setting point of temperature for the top heater and the bottom heater. That means your sample, when it is heated, the top surface will have the same temperature as the bottom surface. So your sample will be in highly temperature uniformity. Then our probe go into a hole on the top heater to get to the top heater and get contact with the top layer of our, top sample of our sample, top surface of our sample, sorry. So in this case, you can see that we typically have a long shaft probe for a high temperature test. That means it is very challenging for performing a scratch test at high temperature, because your probe is very long now. So if you perform a scratch, your lateral force will it creates a very high momentum, and your probe could be broken easily. So for interfacial stress measurements at elevated temperature, we can use indentation test. So this is the very first example I'd like to share to you. So you can see we have the wafer 2 and the other one, wafer 6. Their interfacial bonding is different, and we can perform indentation array to induce debonding locally, position by position, and then we can control the temperature. So this is the room temperature, and 100 degrees Celsius, 200, 300 degrees Celsius. And you can see that obviously your critical force, which is the required force to delaminate the interfacial, the interface decreases when the temperature is going up. That means your interface is getting weaker at higher temperature. Similar behavior can be found at another wafer, and we can get the critical load results changing with temperature. So changing with temperature from room temperature up to 300 degrees Celsius. And for these two wafers, the tendency is the same. The trend is the same. I mean, the temperature is going higher. The critical load is going down. And this is only can be done by the indentation test, because we are using our heating stage. And very finally, I would like to give you this example of polymer. This polymer is polyimide, have a thin thickness of around, should be 10 micron. And this is a structure like this. So you can see that the copper is the conductive there, and the polymer is here, which is an insulator for insulation. And the interface between copper and polyimide is typically a challenge point. So we are going to investigate them. And why we need to have a different temperature? Because believe it or not, when the manufacturing process of the copper, which is actually a high temperature process. So the temperature can go up. I mean, when want to deposit the copper layer up to the polyimide, the temperature can go up to 200 degrees Celsius, which is actually quite high for polyimide because, as I know, polyimide has a glass transition temperature around 230 or 40 degrees Celsius. So yeah, 215 degrees Celsius, I would say, to polyimide is very high temperature. And you can see that this is the indentation induced delamination. So this is the delamination point, and this is the critical low. And we have 3 different temperature levels. Obvious, at a high temperature, the required force to delaminate the interface is going down. That means your interface is weaker at high temperature. But interesting thing is if you can take a look at these indentation curves. So we use exactly the same probe and apply exactly the same force. And you can see the penetration depth is also highly sensitive to temperature. At higher temperature, the penetration depth is getting higher. That means your mechanical properties of your polyimide layer is going down when temperature is going up. So we can measure because this is indentation test, we are able to measure the modulus and hardness together at the 3 specific temperature levels. So we can see that both the hardness and modulus go lower when the temperature goes higher. So yeah, please.
So we need to follow the 10% rule?
Yes, exactly. Good question. So the key point is we need to avoid 2 things if we would like to collect the mechanical properties of polyimide. In this case, one is the substrate effect. So we are not able to go very deeper. For example, the thickness of polyimide is 10 microns. That means we are able to, we are focusing on 1 micron penetration depth to follow the 10% rule. The other thing is we also need to avoid the adhesion happen because the structure is damaged. I mean, the interface is failed. So, on this arm, the sample changed dramatically. So we are not, that means these 2 sets of hardness modulus for the top layer of PI are collected in this small penetration depth and before interface debonding happened. Yeah, thank you. Good question. And we do that because the critical low actually not only related to the interfacial strength, but also related to mechanical properties of the top layer. So if we would like to, have the intrinsic interfacial bonding changing with temperature, we need to apply this formula to calculate or to convert the so-called strength energy release that G here. G is named after Gibbs, Dr. Gibbs. So sometimes you will find in some literature, it is called Gibbs energy, but it is not really energy. So if we take a look of this, for categorization of interfacial bonding, the intrinsic property has a unit like this. So typically we say Gibbs energy, but it is not really energy. You can see the unit is joule per meter squared. So for me, a good understanding is this the value is a property that's delaminate the energy, the required energy to delaminate a area of 1 meter squared. So it's something that, so for I just want to emphasize that for interfacial bonding, the property is not force, it's not pressure, it's not energy. It is very special. I mean, quite special for a beginner here. So apply this one, and yeah, for applying this formula, you will find, sorry, there are two additional values required. One is the A, which is the denominated radius, in this case, radius. And the other one is R. R is contact radius. And yeah, typically it is not so easy to determine. And for this case, we are lucky because the top layer of polyimide is transparent. So when delamination happened, we are able to see. So this is a post optical image. So you can see the dark inner circle. I would say circle means the contact area, contact region. And we have another very interesting bright outer circle, which is the delaminated area. So we are able to determine these two key radial values according to the post-optical image. So everything is ready for this calculation of Gibbs energy. Then we have the results here. So this is the interfacial bonding changing with temperature. So it is room temperature. This is the slightly higher than 200 degrees Celsius. So you can see it is very different. So if you look at, we have two data sets of the related to the delamination. One is the critical load changing with temperature. So you can see, yeah, very interesting. The critical load is quite linear. I mean, decreases linearly with temperature. But if you take a look of the Gibbs energy changing with temperature, it's very difficult. Yeah, because your hardness and modulus also change dramatically with temperature. So we can see that there are, I would say there are two different slopes. One is below 150 degrees Celsius. The interfacial energy is not decreasing that much, but when the temperature go up to 150 degrees Celsius, it drops, the interfacial energy drops very significantly. So it is a very bad news. For metrology, this is a good news. But for, if we go back to this one, yeah, for manufacturing of copper and polyimide, it is a very bad news. That means when you have a high temperature process up to maybe 200 degrees Celsius, your interface will get much weaker than room temperature. So yeah, this is the final example application I would like to share to you about the interfacial bonding metrology at elevated temperature. So this is the takeaway. So today we are talking about the indentation together with scratch, of course, focusing on the intrinsic mechanical properties of the top layer and the interfaces. Yeah. Thank you so much. Yeah, please.
Running the sample dealing with is extremely hard. For example, it's a diamond. Your sample is a diamond or layer.
Good question. Yeah, because typically we use a probe made of diamond. Yeah, because the diamond is probably the hardest one, and the modulus of diamond is also almost the highest material that we know that we can get. So if you want to use a diamond probe to test diamond sample, I will say it's doable, but your probe will have a very short life.
Yes, yes.
Yeah.
But, I mean, when you're doing the measurements, because your modulus of your sample is very
Similar to the
your
other.
indicator, so what if anything will change?
No, actually, theoretically, I would say sorry, I didn't go through the details about the indentation, but I would like to emphasize it here. Yeah, because this is originally a working video. So the modulus provided by an indentation test is so-called reduce the modulus, not Young's modulus, reduce the modulus, which is actually a kind of combination of the samples modulus together with the probes modulus. So theoretically, it is no problem. I mean, if you want to, use a samples of diamond to to perform indentation test, it is okay. But yeah, I have some experiments, and it is very probe consuming, I would say. Another similar experiments I would like to share to you is there is a material called diamond-like carbon, so-called DLC, which are quite common. I mean, quite common in Taiwan. So because we all know that diamond is actually the carbon atoms, which is the same of carbide. So it is a very interesting viewpoint that if you have a middle mixture thing of diamond and the carbon, that will be quite, I mean, interesting for a long time in semiconductor industry, because if you take a detailed look at these two materials, diamond has very high mechanical properties, but diamond is not conductive. But carbon has very low mechanical properties, but carbon is conductive. So if you have something mixture, that will be, I would say, very potential to semiconductor, because sorry, I would like to go. Sorry. Because if you take a look of a structure, no matter how complicated structure of a semiconductor product, there are only maybe two things. One is conductive material, the other one is insulated material. So if it's just imagine that we have a very good control capability of DLC. That means, for conductive layer, we can use a carbon, very carbon DLC. But for isolator, we can use a very diamond DLC. That would be very convenient and very cheap. Yeah, it is believed that, but it is have been developed for decades, but still not so easy to I mean, for quality control. But this is a very good question, because I do test a series of DLC samples, and some very diamond DLC will consume our diamond probe very quickly. But it's doable, I would say. It's doable. Any questions are welcome.
So you cannot use a very good. This kind of test.
Yes. I would say because we are the same company, but different product lines. I mean, the answer is yes. I would say the main gap or main differences between FM mechanical, I mean FM based mechanical metrology and the indentation based mechanical property metrology. I would say the main gap between these two is the range. For because Dr. Tao has the range overview. It's just a quite similar thing. For indentation test, the force range is from maybe several tens nanonewtons to millinewtons or even to newtons. Yeah, but for FM, typically you will see the unit of piconewton, but not nanonewton. So I would say these two metrology, these two product lines are very good. Both are very good, but the range are different. And you can see for indentation test, we are doing, I would say, we are always doing some damages. Yeah, it's something we love to do to damage something to
So
expose.
here actually the minimum thickness you mentioned like 50 nanometer. And for this we need to apply 1.5 nanometer.
Yeah.
Like if we want to find the elasticity or hardness.
Yeah.
But like if the film thickness is say 1 nanometer,
Mhm.
then we have to use a film.
Yeah. If
So it's not possible by this.
so far, not. I mean, nano indentation is not doing a very good job when the penetration depth is smaller than 1 nanometer.
So like it is same for AFM as well. Like if it is if the film thickness is 1 nanometer, then I have to apply 0.1 nanometer. Like then
yeah, you need to 1 angstrom penetration depth, and I
That's
will.
also not possible for FM to achieve just.
Yeah.
So if you film, if your sample is less than maybe 10 nanometer, several nanometers, then you cannot get it is a magnetic property by application on the substrate. For 2D materials, some researchers they using a substrate with some holes and just
they transfer the
they transfer the 2D material on the hole, just penetrate. And the difference of FM and another inventor, well, force measurement is a very common question when you come because we both have for force measurement, because this symposium we are focused on force measurement. From smallest force is optical tweezer. We're going to 0.1 piconewton to several
Nanonewton.
piconewton to maybe only 1 or 2 nanonewton.
Nanonewton.
So the maximum force for optical tweezer is several nanonewton. But for FM, we goes to from maybe tens of piconewton to hundreds of nanonewton or thousands of nanonewton, which is micro.
Micronewton.
Yeah, but that's the up limit. And for nanoindentation, goes to maybe tens of nanonewton to
millinewton or even to newtons.
Newton. And above that, we have a tribology test.
Yeah.
You can go to maybe 100 nanewton, millinewton to thousands of newtons. So it's different force range, you need different technology. So there's no technology or product can solve all questions. And the difference between FM and nano-indenter, besides the force range, there are two other factors. The first one is lateral resolution. FM, this is advantage of FM because it has smaller probe. The diameter of FM probe it can go down to 1 nanometer or 5 nanometer, or maybe 10 nanometer, 20 nanometer. That's much smaller than the diameter of this nano-indenter probe. So it get a higher resolution. And they can apply smaller force. But the one very critical drawback of FM for force measurement is the FM use cantilever, so it has a optic level. They are actually measuring the bending angle of the AFM cantilever. It's not like a direct force measurement of force sensor. So theoretically and practically, it's not the same. Yes, another indentation, you can always get a more accurate, more repeatable data, force data when the force is in the range. So it's like just two technology, not competitive, but complementary. So you need to buy both data. It's different. Any other questions? If not, let me sex.
Yeah.
And again, I would like to express my gratitude towards Dr. Selena Golden and SPM of Company USD, and also High-Tech team. Everyone. Thank you very much. Thank you. Maybe like take a group photo together.
我微博没有开画图。
2点钟是吧？
Thank you very much for asking questions.
没有，我听见了当时。对，就是可能在之前开过。